Sorry, it's going on.
Yeah.
The lamp is already on. It takes some time. Take your microphone. It's already on.
I should probably switch it on somehow.
No. Okay, just a short announcement before the start of the class. We have scheduled the afternoon session. There's only one afternoon class this afternoon. We have scheduled that on 5:30. That's it. Yeah, 5:30. So after 7 o'clock. And we have a little bit longer time. For example, also for hiking. It seems that the weather is good tonight. Poster session. We plan to do an official poster session on Thursday, next Thursday. However, this should not prevent you from already putting on the posters from Monday on, for example, in the poster room. So try to organize it a little bit yourself, so everybody has some place. We can also use the floors, the corridors, but just please, if you put on your poster, just on the doors, because otherwise, the walls would spoil. So you can also already before the official poster session, just discuss among you around the poster, so that you have your, you can do that informally in that sense. Okay, so start.
Yeah.
Just another one. Don't forget to sign in for Sunday. This is now the Sunday sheet. You just some of you have already filled it in.
Right. Good morning, everyone. So we should remind ourselves where we are. And basically we are, this week we are trying to finish off this single particle problem for relativistic particles and how they are modeled in graphene. And this is what we talked about and also what we'll talk about today. So it's an interesting situation that relativistic quantum mechanics has been developed in 1930s, and very soon after the Dirac equation was introduced, people looked in how external fields alter the behavior of quantum relativistic particles, and predicted various phenomena, some of which were demonstrated, but most of them have not. And it is probably still out of reach. Many of these phenomena are still out of reach for particle physics, especially the ones in strong E and B fields. Even classic phenomena like Schwinger pair creation process, sparks in a vacuum, that are created by strong electric field and various others. So luckily now we have a condensed matter system where we can do reliable experiments with relativistic particles. That's graphene. And so basically what some people like me have been doing is taking a relativistic quantum mechanics textbook and then going chapter by chapter and seeing what does it mean for graphene. And so these are various topics that we discussed in that spirit. Each of them, Klein tunneling and how you detect Klein tunneling by using pi phase jump and a back reflection, and then the relativistic motion and constant field and its relation with p-n junctions, and then two different regimes for relativistic particle and strong electric and magnetic field, where there is a interesting difference with non-relativistic particle, because in non-relativistic particle we know that if you have electric and magnetic field which are orthogonal, you can always eliminate electric field by going to a moving frame, moving with a drift velocity, and that leaves you in a co-moving frame that leaves you with magnetic field only, and you basically, for quantum particle, you will have Landau levels, but in the presence of a tilted potential due to electric field. In contrast, here we have two regimes, because as we know from special relativity, if you have E and B, you can eliminate either of them depending on which one is bigger. And so there are two regimes, electric and magnetic, and in one case you have Landau levels in the tilted field, but in the other case it's equivalent to a pure electric case. And so this is all well known from special relativity and simple combination to quantum mechanics. And so in this regime one can see what some people call Landau level collapse, that Landau levels that you see in magnetic regime collapse when magnetic field becomes weaker than a certain threshold. And all of that can be demonstrated experimentally. This is a plot from experimental paper. You can see all of these, both of these regimes, and also the pi phase jumps that appear here as half a period shifts and Fabry-Perot resonances as you increase magnetic field. And then on this side there are no Fabry-Perot resonances, there are Landau levels, but as you can see, Landau levels only exist above certain threshold, and they don't form the conventional Landau fan that starts from zero density, zero field. Instead they converge to some point at a finite field. And the reason is just that there are two regimes, magnetic, which is found here, and electric, which is found here. So, all this is very basic and interesting at the same time. And I decided to present it as an overview, not talk about each of these problems in great detail, but rather, show the whole variety. And obviously there are details that we skipped, how calculations are done, etc. And each of these problems could be expanded in one lecture with full derivation, but I think it's more important to see the big picture and not the details, because single particle Dirac equation is a textbook thing and can be analyzed. But
Schwinger pair creation phenomena. You mentioned briefly that Schwinger pair creation phenomena were not observed in QED.
So we'll get to that in a second. Yeah. So I just want to explain I want to explain the plan before we get to any of the details. And so the plan is just to take these quantum relativistic problems and see how many, which of them we can see in graphene. Some of them have already been studied experimentally, and in particular, the ones which are boxed here have been demonstrated. So I will continue in the same fashion today. Try to be brief and not get into the details. But please ask questions. I think giving an overview is a better format than giving a detailed Blackboard presentation of any of these problems, because big picture. I think here the big picture is more important than details, as in many other cases perhaps. Someone said that one of the great poets said that the most important thing in poetry is to aim high, and then the details will follow, right? So I'm not trying to compare anyone with any. But
did Landau say anything about this issue?
Well, Landau said many things that better not be quoted. But so what did you?
I was wondering whether Landau had made some statements about high versus details. What to do first.
Russian poet.
Yeah, poet, right. So I'm thinking about Brodsky, but yeah, whatever. He's also Nobel laureate, but not in physics. Right. So, and so please stop me and ask questions whenever you feel good about it. Actually, and I perhaps let me see. Maybe I should ask a question. Yeah, can I maybe take 5 minutes and abuse my position of lecturer and ask a question that I wanted to ask yesterday? Okay. It's a philosophical question, so the answer may not exist. But so it has no relation to this. But I was after afternoon lectures by John Chalker and Bernard Dissot, I was thinking that there is a similarity on some deep level. There is a similarity in what they're talking about, even though one is statistical mechanics problem and the other is quantum mechanics problem. One is many-body, the other is multi-spin. But in both cases, there is a highly degenerate ground state with entropy in one case and high degeneracy in the other case, and various methods are used to handle this degeneracy and understand what kind of ordering we get out of that out of that degeneracy in the presence of weaker interactions. And so, I don't care. I'm told to care about my reputation, so I'm allowed to ask silly questions. Is there any relation beyond just verbal between these? Quantum Hall is a unique, we think about as a unique system with very special properties, analytic functions, holomorphic, meromorphic representation, very beautiful but also unique. And then at the same time, in spin systems, we have a large variety of different systems that all show in some broad sense this behavior where out of large degeneracy you can form new order. And so can quantum Hall be thought of a special case of that, or is quantum Hall maybe a mother of spin liquid, or what? There may be some relation between these two, because high degeneracy interactions that produce something interesting out of it. Does anyone know?
Well, I think at some level there are common features. So in the models of spin liquids, if you go to quantum bonds, then of course we'll be hearing they have topological orders. So in that sense, you've got something in common with fractional quantum Hall systems.
Yeah. You'll talk about it?
Yes.
Okay, good, great. Sorry. All right.
But maybe other people have comments on the similarities or differences.
Yeah, one comment that in models like you can have loops. Like in many spin systems, you end up with constraints. Like for example,
Of course, yeah.
You can follow. You can write as a theory of loops.
Of course.
So maybe not in quantum Hall, but in double theories. Like for example, in theories like double sounds like, for example, the toric code is a theory of two kinds of loops. It's also a double chunk Simon's theory. So there you can have the connection of anything that has constraints and anything that the excitations are extended objects. But I can only know how to do this like model by model, but not like a comprehensive view of how to say that. That's
right. So what John said is that in spin liquids we can model quantum Hall, and then what you said is the is the opposite. So still wondering what exactly is the relation. Yeah.
Actually, I have a question about this in turn, because the question should we be surprised, because if we have this degeneracy, what this means is that some of the single particle effects don't matter so much, and therefore correlation should matter, and interactions. And then we should not be surprised to get some states which are described by long-range entanglement, it seems, like Chang Wen told us about. And that seems to be some of the connection between the two, right? I don't know if this is
no, I subscribe to that, but I would like to see more precisely what's going on. Yeah. All right. Anyway, so let's. Right. So I just wanted to bring this up because I think it's an interesting discussion topic. So the Unruh effect is also an interesting discussion topic rather than a result. I unfortunately don't have a paper published on that, but I would like to. So let me talk about it in that same spirit. It's a discussion topic. So the Hawking Unruh radiation. Let me remind you quickly what this is. You remember Bekenstein-Hawking entropy and temperature and radiation for black holes, right? So soon after that, these results appeared. Unruh proposed a simple model to help understand that, which doesn't uses gravity in a very minimal way. So there's no black hole in it. Instead, there is a thermometer or detector which is accelerating. And then using the standard argument from Einstein that accelerating lift models gravity, and by general relativity principle should be in all ways equivalent to gravity, Unruh looked into what accelerated detector will measure, and sure enough, he found that in full agreement with general relativity, it will measure even if it's accelerating in vacuum, it will measure excitations at a finite temperature, which is proportional to detector acceleration, and is given by this formula known as Unruh temperature. I think someone Davis derived it even before Unruh, but anyway, so this is known as Unruh's temperature, and it's an interesting phenomenon because especially from the point of view of probing phenomena related to black holes, we wouldn't like to get too close to a black hole. So if there was a way to probe these effects, the black hole effects, without actually traveling to a black hole would be very nice. So what they say is that all you need to do is take a thermometer and accelerate it. Yes?
I don't get, where did the excitations come from? Like, where do the excitations come from? Just like one observer in vacuum moving, or shouldn't there be?
Yeah. So I will. I mean, I'm not going to show a full derivation. One can show a very quick, sloppy derivation of the effect, which I'll try to do. But let's postpone a little bit. So what they say is that if you take accelerating thermometer, it will measure a finite temperature, and that temperature will be an analog of Hawking radiation temperature. And well, this is obviously immensely interesting, and it started lots of discussion in the literature whether the thermometer which measures temperature will radiate as a black body, and what will happen to stations of bosons and fermions, etc. And then, after all that has been sorted out, and at the same time, there was a question whether that really makes it easier to detect these phenomena, because if you work out an acceleration that you need from this formula to get a temperature of, let's say, 1 Kelvin, then this acceleration will be ridiculously large. It will be billions, billions of whatever units you take, so a real thermometer will not survive that. But then there was a paper published in '82 by Bell and Lenas, same, Bell's inequalities, that made an interesting proposal. They said that if you, instead of thermometer, use an elementary particle. Elementary particles are, to a large extent, indestructible, and so you can accelerate them and they don't break. So if you take an elementary particle with inner degrees of freedom, you can use inner degrees of freedom as a thermometer, perhaps. And so what they considered, take an electron and accelerate it, and then electron got spin. So if this electron will see vacuum and its accelerating frame as a space filled with radiation of finite temperature, then there will be a spin temperature of that electron that should be detectable. And they made the estimates, and it turned out that using modern accelerators, they both worked at CERN, very close to here, and they made estimates showing that even though acceleration you need is ridiculously high, with modern accelerators you can easily achieve that, and you can get to fields which correspond to Unruh's temperature of a few thousand Kelvin, so it shouldn't be a problem at all to measure it. However, then looking further into it, they discovered that there are various artifacts that would prevent you from actually doing this measurement. One of them is that accelerated electron radiates photons at different rate in different spin polarization states. Let's say if you're thinking about synchrotron electron going around in a circle, synchrotron radiation depends on spin orientation. Actually, in a synchrotron, you get spin polarization out of nothing because of this effect, and it's much quicker than the rate at which this Unruh's imbalance builds up. And similar problem I encountered at linear accelerators. So they end the paper saying that, sorry, not possible. However, I think it's a very promising idea, because indeed elementary particles are much less destructible than any thermometer you can buy on the market, and so we can think about it again, given that we have relativistic effects in graphene. And let's say we can take graphene p-n junction, which can be modeled by a relativistic electron in a constant field, and make an estimate. And so what comes out is that electric field is not as high as in accelerators. However, the mass is much smaller. The role of mass is played by this band gap that opens up, which is a few hundred Kelvin for graphene, let's say, on boron nitrate substrate, as we discussed yesterday, the day before yesterday. And then also, instead of the speed of light, you have graphene Fermi velocity, so it's another factor of 300. And so it turns out that conditions are as favorable or even more favorable than accelerators, and plus you don't have the synchrotron radiation problem. So one can look into this and think what kind of effects we can observe. And I mean, there is a small difference with this case, because in graphene, a relativistic electron doesn't have spin; it only has pseudospin. So because the wave function is 2-component, not 4-component, so we'll have to use the pseudospin instead of real spin. But sure enough that I mean, it will play a role, but perhaps will not be too crucial. Right. So I mean, if you want a reminder of what we talked about in the context of a relativistic particle constant electric field, it's here. But basically, if you follow the analysis and then you can do it WKB way, or exactly by mapping a Landau-Zeno problem, what you find is that transmission is exponential of a gap divided by what corresponds to Unruh's temperature in this case. So potentially it can be done. However, there is no concrete proposal of what to observe and where and how to look for it. So I think it's an interesting topic. So
I'm just
yeah.
because you say, it seems to me that the essence of the phenomenon is that you have a density matrix which looks stable for the pseudospin degree of freedom, and how the parameter, the temperature, can
so
as a purely coherent quantum mechanism.
Yeah, so let me, okay, I think this will be on the slide. So I need to answer two questions. So first about Schwinger pair creation, it's related. So if we have electron in a uniform field, this is the mass term, and then there's electric field. Then this is band diagram with this is gap. This will be Dirac particle. This will be anti-particle branch, and so it will look like that. And so if I take a state here, which is incident on that classically forbidden region, it will tunnel through it and partially will be reflected. And so this transmission through the classically forbidden region, which defines conductance of a p-n junction, is in fact mathematically equivalent to Schwinger pair creation, because if you take, and it's the same problem. You have a relativistic electron, constant field applied, and Schwinger would work in a vacuum. For Schwinger problem, we work in a vacuum where all these states are field, and there are no states here, right? And so in this case, you see that there are particles and antiparticles created that propagate away from each other, and in condensed matter we have a chemical potential which defines ground state that all these states field, also in these states field. So we do experiment by applying some bias, and so we observe dynamics near the Fermi level, and but mathematically it's the same problem. So in principle, Schwinger pair creation is built in every graphene p-n junction, but again, one needs to find a way to exhibit it.
And how in this language should I view the fact that isospin density matrix, reduced density matrix is thermal?
Yeah. So if you, So let's, So then, if you, I'm not saying it's thermal. No one did calculation.
Okay.
But it's quite plausible. I mean, clearly in each process like that, if you forget about correlation between these two states, which you should do because they're going, they become macroscopically separated. If you think about each tunneling event as a process in which correlations between particle and antiparticle become irrelevant, then you create mixed state, and this mixed state will have some entropy and perhaps some temperature, and so yeah. So that's the idea. I'll come to that. Right, yes.
Is that not just some breakdown effect?
What?
Is that not just some breakdown effect?
Yeah. So this is well known in condensed matter, and maybe even before Schwinger worked on it. Zener worked on it, and it's known as Zener tunneling, Zener breakdown. Yeah. In Zener's case, however, the bands were not part of the same matrix Hamiltonian. So Zener worked on a problem where you have a semiconductor with one band and maybe the other band out here. They could be lined up in K-space or not, and so he considered field tilting it and tunneling, and that's also a very interesting problem, closely related to that. And then after Zener, some other people modeled Zener breakdown using relativistic Hamiltonian. So in principle, it all can be found in the literature. There is an old paper by Aronov and Picus. Not Aronov of Aronov bomb oscillations, but Aronov of Altshuler Aronov that used this type of model, but in 3 dimensions for Zener breakdown. Anyway. So that's that. Then there was a question: can we understand something? So the question, as I read it, is: can we understand something about Unruh radiation without reading Unruh's paper? Right. So Unruh's paper is indeed very long. 30 pages long, and mostly about Hawking radiation, and then there is a small paragraph at the end about this, but it's hidden very deep in that other discussion. So there are simple explanations of Unruh's effect, and maybe the simplest one is as follows: if you think about accelerating particle, special relativity space-time diagram for accelerating particle will be as follows. You write in a constant field that produces constant acceleration. You write equations of motion. It will be electric field, and then here there will be some Lorentz. Some Lorentz factor. I think it's 3/2. So if you solve it, then you find a trajectory which can be conveniently parameterized by proper time, and trajectories look, as a function of proper time, they look like that. So there is and then here it's it should be MC square and some units. So it should be how do I do it? So there'll be something here and something here that is made out of MC square and other constants, and then the trajectory of accelerating particle is a hyperbola looks like this, and then this offset is this is what goes here, so it should be proportional to mass divided by electric field. Yeah, I guess it should be mc squared divided by electric field. So, yeah, so that's right. And then this one will be mc divided by E. Yeah, so it's a hyperbola, and so what you see from that is that this particle can communicate causally only with region in this wedge. It's called Rindler wedge. And then, all events here, information sent from them. Let's say if there is an event here, then information sent from them, light cone, will never reach the particle. So for accelerating particle, there is a horizon from the causality point of view. And it's this horizon that is analogous to black hole surface, right? And so that's good news. Furthermore, if you do a simple calculation, so what people did to derive Unruh's radiation, they take a many-body Hamiltonian describing some elementary excitations, photons or something else, and then transform it to accelerating frame, and then show that vacuum, zero temperature vacuum in a lab frame corresponds to finite temperature state in the accelerating frame. But you can do it simply. You can say something like this. You can say that let's take this trajectory, and also let's take some plane wave with frequency omega and momentum k, and maybe let's take them in the relation omega equals ck, so it will be a photon, and then take this plane wave, which will be this in a lab frame, right? And then look at what this plane wave is in the particle frame. And basically, what you need to do is to write down a Lorentz transformation relating this and that. And schematic, I don't want to do it in detail. Basically, I want to do this, and then after you do some algebra, you find that in particle lab frame, this is seen as e to the minus I omega times e to this number. So in particle lab frame, you see particle will see this wave not as a constant frequency wave, but as a frequency wave with a frequency which varies with time, and it's equal to that value at tau equals 0 when particle is at rest. But then at other times, this describes Doppler effect. It describes frequency which is higher when particle is moving opposite to the wave, and lower particle moving. Yeah.
Sorry, what happened to the K?
Yeah. So I'm taking omega and K are related like this, and then here I plug in cosh, and here I plug in sinh, and then cosh plus sinh combined to give exponential. I mean, one can do it more carefully, but at the end, so you need to do some Lorentz transformations in between, but at the end this will be a result. There will be a time-dependent Doppler shift. And then if you take this and Fourier analyze, ask what's the spectrum. Sorry, yes?
Time that I understand that, and it's not homogeneous, your argument. Is it the time MC over E, or is it tau?
So originally I started in a lab frame, and I took plane wave which had some space-time structure, and then I specialized to what particle will see. And so I have to take that plane wave, transform it to particle frame, and then take it at particle position. And I skipped some algebra, but you can get the same result simply by putting these equations in here, and then this is the correct answer.
Yeah, but it's not homogeneous. You are
That's right, because particle will see wave which is.
No, I mean it's physically not homogeneous. The argument should be of dimension 1. It is the dimension 1 of the tau, 1 over time.
Oh, yes, of course.
It's an MC over E.
Right. So there'll be this number that will. Sorry. Yeah, there will be this number that I need to copy over here. Right. Thank you. And right. So then, I mean, all you need to do that. I don't want to do it on Blackboard because it's kind of simple. All you need to do is take this and take Fourier spectrum and ask what's the radiation spectrum that particle will see, and if you take G of omega defined as as a Fourier transform, then, I mean, this integral is easy to calculate because it's a gamma function. I mean, you can reparameterize it using this variable, and then using this variable, it will become an integral from 0 to infinity, and this will become a power law. So you'll get some u. So I'll call this variable u. It will become u to the power I omega. I guess times this number again minus 1, and then this will be e to the minus I omega, this number, times u. So you get an integral which is a gamma function, and then taking the intensity, taking the spectrum, square modulus of the gamma function will generate a Bose distribution. So G square modulus will be up to some factor 1 over E beta unrho omega minus 1. It's very simple. And then the many body calculation that you find in literature basically follows this idea, except that they start with a many body operator, but then when you do the analysis, you find that each elementary excitation contributes independently of each excitation with a different momentum contributes independently of other excitations, because plane waves with different momenta don't mix. And so you find the same result, but for an ensemble. Yes?
What is U and what is G?
U, forget about. I mean, it's a very simple calculation, easy to do. Just plug it in the MATLAB and it will give you a gamma function. Sorry, not in MATLAB, in Mathematica, Maple. All I'm saying is simple. I mean, I'm not.
And in what way would this change if you use a quadratic dispersion, for instance?
So this is relativistic. So it only works for linear dispersion. Quadratic dispersion, totally different story. I'm not talking about it here. But yeah, if you look into this for quadratic dispersion, it becomes totally different. And it's not in textbooks, so we have to do it from scratch. But for relativistic case, it's all in textbooks, so we just need to read it and then transplant to graphene. What?
I don't see where the physics would break down if you use the quadratic dispersion.
No, you can do calculation, but you don't find anything simple. You don't find.
Okay, so it's more complicated.
So, for example, I mean, this problem of Zener tunneling, right? So, for the problem of Zener tunneling, you don't find anything that looks like exponential. You find something very complicated. You find that in the. It's also interesting, but not not from the point of view we're discussing here. If you just, in 30 seconds, let me say, if you do Zener tunneling for quadratic spectrum, like in graphene bilayer, you find that on the barrier there are several paths that give a saddle point solution, and miraculously these paths have exactly the same actions, so you can't say you are dominated by one of them, so you have to take contributions from several paths, 2 in particular, and also the action is complex, so it's not real, it oscillates. One of the paths gives exponential decay with phase oscillating clockwise, and the other gives exponential decay with phase oscillating counterclockwise. So as a result, you get instead of Zener tunneling, you get Zener interference on the barrier, and it's totally different from what you get for a linear case. And surely everything else will follow from it will be similarly different. But let's not get into this. Yeah.
Sorry, I think I missed something. When you take the Fourier transform of the proper time, why did you do that?
So I want to find, I'm thinking about classical field, and I want to find what will detector measure. Detector will give me, my picture of detector is that detector gives me spectral distribution of whatever signal comes to it. So I have to Fourier analyze and take spectral density. And that's, I should do it on a quantum problem also, but the essence of it is captured by this classical analysis. Yeah.
So okay. What you've calculated there is an intensity, and you find some sort of bosoning distribution or ozone distribution. Just what is beta here? It's not true temperature, right? It's related to the tau. Can you write down what beta is?
Yeah, so it's inverse of this number that we defined previously.
So this is where this unknown temperature comes in. Okay.
Yeah.
Sorry, there's something basic I'm confused about. So this intensity you've written as a function of capital omega, but the expression on the right has small omega in it.
Oh, sorry. Yes,
It should. There's an omega in G, a small one.
Right. Sorry. Right. So it will be. Yeah, so it should be a capital omega, and little omega will. Yeah, so this should be a capital omega, and I think little omega will appear here. Yeah, I can look it up. I have this paper in the computer, but let's do it later. I don't want to do it now. Yeah. Yeah. Anyway, so I was talking about only in way of saying that there are more things there to be looked at. No results on it yet, but I think it's interesting because if we get to probe black hole physics and without traveling to black hole, even in this very simplified way may be interesting. Yes?
So in this case, to observe this other effect, you need to have a mass gap in your graphene?
Yeah.
I mean,
Yeah.
if you don't have...
Yeah, then nothing, yeah. But then, yeah. Well, okay, so it's not entirely so, but you better have mass. I mean, if you want to realize Bell-Lenas proposal, mass is good.
With the smaller the better, because the temperature is higher?
Well, smaller, but you don't have to, you're not bound from that side, because if you put in numbers, you find that you're okay with whatever mass you got. I mean, this 100 Kelvin mass will be fine.
So for graphene, what is the scale of under temperature for a typical setup that you have in mind? Or?
So I'm thinking about it from a different point of view. Because as we just discussed, the effect is related to Zener tunneling or Schwinger pair breaking, whichever point of view you prefer. Basically, what you need to see is tunneling through p-n junction, which exponentially depends on electric field, and it's always like that. So whatever you build, you get tunneling, which strongly depends on electric field, and it's there. So you need to work very high. You need to make the electric field very, very small to suppress this tunneling. So I think it's always there. The question is not how to reach this limit, because it's already there. The question is what to measure.
That's how you extract the number.
Yeah. How do you measure temperature? Yeah. Okay. So let me talk. Okay. So this is. Oh, I'm already in the second half. Right. So let me skip preliminaries. There is one more, so the last one, quantum relativistic phenomenon that I would like to talk about, and that's atomic collapse. So this one has been measured, and let me do a very quick introduction and explain. Again, it was discussed and predicted a long time ago, and then talk about graphene and how it was measured in graphene. So the discussion starts with stability of planetary atom, and we all learned that before quantum mechanics was introduced, people didn't know why planetary atom model was stable, and there have been various ideas about gellium and such that would stabilize atom. But then later, it turned out that quantum mechanics can do it for point particles, and just from Bohr's angular momentum quantization, orbit quantization, you see that atom energy can only take discrete values, and you can make it more formal using Heisenberg uncertainty principle. You can say that if you take electron in the presence of positive nucleus and take its total energy, it's a sum of kinetic energy and potential energy is negative 1 over r, and kinetic energy for a non-relativistic particle is p square, and if you relate p and wave function radius by using uncertainty relation, you get 1 over r square for potential energy, and 1 over r square becomes very large when radius becomes very short, and it overwhelms this potential, and then at larger values of r, this term dominates. So if you take the sum, you will see that it's dominated by kinetic energy in this region, by potential energy in this region, and then there's a minimum, which is the stable state of an atom, and so that's how quantum mechanics cures the stability problem for non-relativistic atom. And this is also not the collapse I'm going to talk about. I just say it because it's on the back of our mind when we're thinking about atomic physics. I'll be talking about something else. And the collapse that we're interested in is the one that arises in the relativistic problem. And so here what happens if you consider classical relativistic dynamics is the following. you find that for relativistic dynamics of an electron orbiting around a positive charge, you get two types of orbits. There are orbits that look like Kepler orbits, which are precessing, these rosettes. And then there are also orbits that form spirals that spiral on a nucleus and descend on it in a finite time, and these are collapsing orbits. And so this was found very early on, not in any relation with quantum mechanics. I think it was first published by, this calculation was first published by Darwin, who was the grandson of the biologist, and also known for Darwin term in QED. So there are two types of orbits. And the threshold between collapsing and non-collapsing is set by angular momentum. Angular momentum larger than this value creates non-collapsing orbits, smaller collapsing orbits. And notice that mass is not involved. So the threshold depends only on angular momentum, but not on mass. And that will be important because it means that we get similar behavior for massive and massless particles, and graphene, therefore, will come handy. So quantum mechanics cures this type of collapse. And then for this one, if you repeat the same calculation, take kinetic energy and potential energy, add them up, and then say that in the ultra-relativistic limit, when momentum is very large, uncertainty relation gives kinetic energy is linear function of momentum, and so uncertainty relation gives kinetic energy, which is 1 over r. You get the sum of two terms which behave as 1 over r, this one positive, this one negative. And so depending on the ratio of the coefficients, they will either, the sum will either behave like this or like that. And the condition for the threshold separating this behavior from that behavior will be exactly this one, but with angular momentum replaced by h bar. Okay, so you get h bar c greater or smaller than z for collapsing and non-collapsing case, and so this intuition actually is right, because you can look at the exact solution of hydrogen atom in Dirac paper 1928 and find that the ground state energy that this paper obtains is given by this form. This is in the units of mc squared, and then zeta is the fine structure constant multiplied by nuclear charge. Then if you if you stare at this formula, you see that when z becomes large enough, you get a negative number on the square root, and that means that your Hamiltonian acquires complex eigenvalues, which means that it becomes non-Hermitian or state collapses, and so you can only, and it's only meaningful up to, the solution is only meaningful up to z equal inverse fine structure constant 137, which is what Dirac found. At the same time, this solution matches very well non-relativistic quantum mechanics solution. If you take z, which is small, and then expand this in small zeta, then the first Taylor expansion term gives you the Rydberg energy for the ground state of Bohr's atom, and then second correction gives spin orbital correction to fine structure correction to that, etc. So in the non-relativistic limit of small zeta, it matches everything we know, but in the high z limit, it becomes bad, right? And so we need to, we have these complex energies, and people worried about what the origin of these complex energies, and there've been a long discussion of that in literature, particularly about what happens when z is larger than 137, so the
question.
Yeah.
What is the largest stable atom atom that we have created for?
That's right. So good. I forgot to say that. So the reason people were interested, actually, maybe let me go to the next slide. The reason people were interested is that in the periodic table we have So currently we have atoms going up to Z 118 or something like that. So it's pretty close. And so it's a natural question to ask what happens if we go to higher Z. And people who worked on it, next generation of people who worked on it, they were also all people who were involved in atomic projects, both in Russia and in the U.S. And so there's probably a reason why this was a topic of intense research, and they were interested in that. Even though it sounds like a purely academic problem, to us, they might have thought about it otherwise. But we don't. I mean, we don't know. I mean, I would love to know, but I couldn't find anything about it. But anyway, so the important observation was made that if you take into account finite radius of nucleus, which is very small, it's 10 to the 4, 10 to the 5 times smaller than Bohr's radius. But nevertheless, if you take into account finite radius of nucleus, not 10 to the 4, it's a million times smaller. You cure the problem. Your Dirac Hamiltonian becomes Hermitian, and then nothing tragic happens at z equal 137. Your discrete state remains discrete, and it continues to descend down in energy until it enters the negative Dirac continuum, which happens at z approximately equal to 170. And so that's a relief, because in periodic table of elements we don't have atoms that go that far. But that's a point where true collapse occurs. That's a point where hydrogen type atom loses the discrete spectrum. Yeah.
Yeah, sorry, I don't get this plot. Like, what's plus one and what's minus one?
So these are energies. These are energies obtained from solving Dirac equation. The energy scale is in the units of mc square. So this is plus mc square, this is minus mc square. This is continuum of electron states, this is a continuum of positron states. And so the discrete spectrum is inside the Dirac mc square gap. And then when z is small, zeta is z scaled by times fine structure constant. When z is small, we are over here somewhere, and then we have discrete spectrum near the top of the Dirac gap, and that's the Rydberg spectrum. And then as you increase z, you go down, and energies go down, and then eventually they dive into negative Dirac continuum, and that's the collapse. Right. So then, of course, people were interested in what happens if z is higher than 170, and can you study this regime? So, yeah.
You made the remark I don't understand. You're saying that when collapse occurs, you lose the discrete spectrum, but you have the impression that levels get absorbed, I mean, just one after the other? Or...
That's right. So some discrete spectrum remains, but at this point you lose the ground state. So the ground state goes in the continuum, and so the people who analyzed this problem, another group of people who were involved in atomic research, and perhaps except this person, but he actually made the most important contribution. I'll come to that. So they analyzed what happens when the discrete state dives in the negative Dirac continuum, and of course it hybridizes with the states in the continuum and forms a resonance, and the width of this resonance depends on position of that energy in the continuum, and they analyzed it. And then there was a question how to observe it, and you don't have atoms with z which is that high, but what you can do, and that's due to proposal in Popov's paper. You can take atoms which are for which Z is subcritical, and but high enough so that 2Z is supercritical. And then if you collide these two atoms together, there'll be a short interval when they form a compound nucleus which is supercritical, and then the supercritical nucleus will create a state which is in the Dirac continuum, and then they said that the state will grab an electron from the continuum and trap it, and there will be a positron emitted, and so there will be a spark in the vacuum that will be produced in such an event, and there will be a particular energy for that positron. So the prediction was to look for resonances in positron emissions, in positron emission in such collisions, and it's being searched for. There have been experiments of that type done in many labs, particularly in Germany, and at some point it was even claimed that these resonances are seen, and then these claims were withdrawn. So I think the status at the moment is that it's not observed, right? But of course, the reason I'm talking about it is that we have graphene, which is where we can do it otherwise. And so, yep. Was a question? Okay. So, yeah, right. So in graphene we have relativistic particles. They are massless, but that's not important because the threshold for collapse depends on angular momentum, but not on mass. It even makes things even somewhat easier because having no Dirac gap relieves us from this problem of discrete levels. There is still a transition going from no resonances to resonances and no discrete spectrum in between. So it's a lot cleaner in graphene, as you will see. So I already talked about the slide at some point. What's important is that because velocity is slower than the speed of light, the fine structure constant is bigger. So if you go from the very same calculation that we did for collapse, you will find that the threshold for collapse is Z over the 1, not over the 100, because of this 300 reduction. And so you expect that in graphene you should see it for charge impurities which have Z over the 1, right? And so that's interesting because that's fairly easy to implement. Also, I mean, there will be some differences because of massless spectrum, and also manifestations of collapse will be different because in graphene we don't, in high energy physics they use nuclei which are naked. They are stripped of all the charge, and then when they collide them, they see some effects due to these naked nuclei altering Dirac vacuum. In graphene, each charge impurity carries its charge with it. It's in the ground state, so we should look for resonances, but they're not going to be. There will be no sparks in the vacuum. There will be nothing tragic going on, or nothing drastic going on. But resonances we surely expect, and then we can look for them, and we can try to understand them in various ways. One can understand them by solving exactly the Dirac equation, which is fairly simple to do because it's a three-dimensional Dirac equation has been solved by Dirac himself for us, and you need to go to one dimension lower. Going one dimension lower means you have two components spin wave function rather than four components. So it becomes much easier. You can also do a WKB type analysis. You can take these orbits that I talked about and put WKB function on them, and then what you find is that for supercritical charge you get continuum spectrum with no resonances, and then for subcritical charge you get no resonances, continuum spectrum, and for supercritical charge you get a family of resonances appearing in the spectrum instantly in in the entire range of energies, and they look like that for positive charge and like that for negative charge. So they look basically like somewhat like Rydberg family, except that these are complex energies. They're resonances due to that discrete level hybridized with Dirac continuum. But like Rydberg energies, they converge on zero and appear abruptly as soon as you cross critical threshold. So this beta, sorry, I forgot to introduce. So this beta is the same thing that we previously called Z, except that speed of light is replaced by graphene Fermi velocity. So beta is Z times Dirac times graphene fine structure constant. Yep.
So what is the slope?
The slope, the slope is some number over the 1. There's no parameter in this problem, so the slope is, I think it's about 1/7 or something like that. Some number over the 1. So anyway, so manifestations of that transition, when you increase Z and cross into collapsing state, should be the appearance of resonances, and so that shows the calculated, the density of states calculated from exact solution of Dirac equation. We can solve it using hypergeometric functions, and then, calculate density of states exactly. And then you see that in the subcritical regime, which means this Z times fine structure constant smaller than 0.5, you get continuous density of states and no resonances. And then as soon as you cross and go to supercritical state, you get resonances, and then depending on how far in the supercritical regime you go, you get resonances at different energies. So here you can see 2 resonances, and here it's 1. So you can make some predictions. Then there was a big question after all that work appeared. There was a big question: what's the value of critical value of Z, and how it is affected by screening that you get in graphene. And there was some long discussion of that in literature. Let me not go into that. Also, there is an interesting question about vacuum polarization, somewhat related to screening, and how that changes when you go to the supercritical, into the supercritical state. And there is a big change, but we'll not talk about it today. There is also a relation to high energy physics, and there is also a question that I will talk about it, but perhaps not today, whether there is a symmetry breaking at this transition. I mean, there is a transition between 2 states, no resonances and resonances, and you can think about it just as a change of state with no change of symmetry, or maybe there is a change in symmetry, and interestingly, there is a change in symmetry. But anyway, so while theorists have been debating all that, experimentalists have been at work, and about a year and a half ago, it was observed, and so experiment was done at Berkeley in Mike Crami's group, and so here is Mike himself looking at the atomic collapse state on the screen of his computer. The idea that was used in this experiment was basically implementation of this Popov's idea. Take 2 subcritical nuclei and make a compound supercritical nucleus. And so I will explain that now. So what they do, I mean, it's an STM scanning tunneling microscopy experiment, and it's a very interesting and difficult experiment. They put impurities on graphene and manipulate them using STM tip, and they've done experiments with different charge impurities, and for some impurities it worked, for some it didn't work. So I will skip preliminaries, only talk about the case that worked. You can take charge impurities which are called calcium dimers, and ask me why dimers later. So you take charge impurities, each of which is bright dot here, and individually they don't produce resonances. They don't produce the supercritical state. But then there is a possibility to move them with a STM tip and bring them together to form compound objects. And when you build clusters, you see that clusters and do STM spectroscopy of a cluster. You see this transition. So, for example, for a single impurity, you can park your STM tip at different distances from impurity. These are crosses, and then vary bias on the STM tip and take IV characteristic, and then DIDV gives you tunneling density of states, and then you see some smooth function. And I can explain these details if you want, but basically the way you should look at it is that there are no resonances here. So it means that in this case we're subcritical. And then if you go,
what about the bump force?
Right. Okay. So all right. So, right. So right. So there is a bump at zero energy, which means that tunneling is suppressed. The reason tunneling is suppressed is that in this experiment they have momentum conserving tunneling. So when electron tunnels from the tip, it tunnels in the gamma point of a brilliant zone at the center, and not in the K and K prime points. And in order to get to K and K prime points, a phonon needs to be emitted. So there is a gap. You have to apply energy which is greater than optical phonon energy. And so this width is of order optical phonon energy, twice optical phonon energy. And it's unrelated to graphene physics. It's a feature of their STM tip. They see it for tunneling in all materials. So it's not, I mean, they always see this gap at Berkeley.
That they have a rather broad tip to
yeah.
momentum is conserved.
That's right.
Along the plane.
That's right. So in all materials, they see that their tip is so smooth they can only tunnel directly in the gamma point. It's not graphene physics, it's a feature of their tip. Other groups can tunnel anywhere in the brilliant zone because their tips are not so smooth. I don't understand. No one can explain what the difference is, but that's how it is. Then also, so basically what you should do is you should mentally try to eliminate this gap by shifting this branch, by offsetting this branch to the right, and then you see a V-shaped density of states. The V-shaped density of states is basically what you expect to see for graphene. The only difference here is that as you get closer to the charge, this V-shaped density of states becomes more asymmetric, right? And then from this asymmetry and how asymmetry increases approaching the charge, you can extract the effective value of the charge that electrons see in the material, right? So you can convert the nominal impurity charge to the actual charge that electrons see in the material, and you can extract that from the asymmetry of the paper, of that density of states, and that's something that we've done. It was a previous paper that I'm not talking about. You can extract effective charge from related to the asymmetry, and just it works really well. So then if you go to 2-atom cluster, you see basically the same thing, except that something starts to showing up here. Then if you go to 3-atom cluster, you clearly see a resonance, and then 4-atom cluster still a resonance, and it gets stronger and moves closer to the Dirac point. And maybe next one starts to appearing. So it looks promising. Also, you can study spatial structure. You can park your STM tip. I mean, what's the worry? I mean, we see resonances. Why are we not happy yet, right? Resonances may occur from a variety of different mechanisms. You can have, for example, inner resonances in an atom, but that's unlikely because we would see it for individual impurity, and we only see it when we bring impurities together. But you can also have resonances which appear when you, let's say, in these famous experiments in IBM by Don Eigler, you corral electrons. You put impurities on the surface of a metal, and then they form surround a little area, and then you get electron waves, standing electron waves in that area, and they are seen as resonances, right? So maybe it's this effect. Maybe there is some electron wave function corralled by 5 impurities, but you can see that that's not the case by looking at the spatial structure. If you park your STM tip on the resonance and then take a spatial map, you see this picture. You see that on the resonance, the signal is spread over a region which is at least 5 times larger than the size of the cluster. So it's clearly not a state which is corralled, but a state which is intrinsic to graphene, resides mostly in the graphene continuum, but is generated by this impurity cluster. Right, so that's good. You can also simulate it, and simulation matches experimental results closely. And so at this point you can declare victory from, on that, and say that we observed collapse. Yes.
So simulation using what?
So the simulation using the same calculation of density of states I've shown before. So you can measure that. You need to use effective charge obtained from this asymmetry. And then you see that transition occurs exactly where you expect. Yeah. So this Z is effective Z obtained from asymmetry. Yes?
Very nice question. If I hear it correctly, you have calcium atoms and you put it on graphene on the sheet, or with a replacement, or how will it achieve the experiment? How put this thing?
Yeah, it's very complicated. There's interesting. It's interesting what they do, and I don't think anyone knows how exactly it's being done. But it's very complicated, because what happens? You see, what happens is that, just to give a flavor, if you put a single calcium atom, it's very mobile, and if you try to probe states, it's ionized, so you get a charged impurity, but if you try to probe states near it with STM tip, it runs away from you, right? So what they do is that some interesting material science. They warm the sample up to, I think, maybe 5-10 Kelvin, and then these calcium atoms start moving around, and when they find each other, they bind to form clusters, dimers or trimers, or etc. And then these dimers are more stable. So you can approach a dimer with a STM tip and do experiment for an hour, and it doesn't run away from you, right? It's single charged. I mean, charge is not doubled; it's single charge. And why is that? Don't ask me. But that's some chemistry of charge transfer between calcium and graphene. And then what's also interesting is that if you do it right, and if the atoms are right, you can push on these dimers gently by STM tip, and they don't break up. You can move them around and bring them together to form clusters, and these clusters are stable, even though each of these dimers is charged. So there is a Coulomb repulsion between these five dimers in the cluster, but they are bound to graphene strongly enough to stay together for an hour or so when you take STM spectrum. So clearly there is some balance, delicate balance that they are relying on exactly how it works, and it works for some atoms, not for other atoms. And I'm sure there are many other details that I'm not aware of. But yeah, no, it's an interesting experiment.
I'm sorry.
Yeah.
Do you see the other elements in the theory?
Yeah.
Around point.
Well, they see it. I mean, the theory is kind of the shoulder.
I mean, does it go down as you increase the bias? In the
It will go down, yeah, but you could add more parameters to the theory to make it look more like experiment. We didn't do that. We used just bare Dirac equation with 1 over potential. That's it. So
you're saying is that a resonances are beyond that?
No, I'm saying that the difference that you're pointing that there is at this and saying that there is a difference, and it's true probably due to simplest model not capturing all the details of the problem. Maybe there is finite size of cluster, which is important, and we model it by point charge. Maybe something else is important. One could add more knobs to make it look more like experiment, but we didn't do it. Basically because we wanted to keep it simple. Right, so let's see, I got 2 minutes. Let me just flash some. Yeah, I think this is interesting and maybe good to say today, and then if there is interest to continue discussing it later, we can talk about that. So there was a question, when we see this transition from collapsing to non-collapsing state, is there any symmetry breaking associated with it? And the answer is yes, and the symmetry that we have to think about is scaling symmetry. Scaling symmetry on the simplest level is when you have similar objects and some of their characteristics like area have a scaling relation with their size, and so it's very simple. You can change shapes, but if you have the same shape, just change the size, then there will be the scaling relation between areas and distances, regardless of what shape is. So that's scaling symmetry when we first learn it. And then from scaling symmetry, one can draw, even on that simple level, one can draw non-trivial conclusions. In particular, if you haven't seen this before, you may be amused that one can prove Pythagoras' theorem using scaling symmetry. The way you do it is that you take the triangle with 90-degree angle and then drop a normal, and then argue that the two small triangles are similar because they have equal angles, and because of that you can write a relation between area of a big triangle and areas of small triangles, and then the area scales as distance squared, and there is some proportionality factor involved, and proportionality factor can be computed using trigonometry, but it doesn't have to be computed because, if you forgot your trigonometry, you can just say that because triangles are similar, this proportionality factor is the same for all triangles, right? And so you can just write this as square of areas multiplied by some prefactor, which is a function of angle, and then because it's the same, you eliminate it, and you get your Pythagoras, right? So that's scaling symmetry, and in the Dirac-Kepler problem, there is also scaling symmetry, because if you look at the kinetic energy and potential energy, this is Dirac electron in the presence of charged nucleus. Then if you make a scaling transformation and take into account that gradient scales with inverse distance, and if you rescale energy by an appropriate factor, you go back to the same problem. So formally, and there is invariant, of course, that this symmetry preserves, which is the ratio of this coefficient to that coefficient. That's fine structure constant. It's my beta. So we have the symmetry, and then from the symmetry we should be able to draw conclusions the same way as in the case of Pythagoras' theorem. So one conclusion you can draw is that all quantities which are scalars, dimensionless scalars, should be scale independent, and that also means energy independent, because if you rescale energy, that equivalent to spatial rescaling, and so we don't expect for quantities like scattering phases, for example, to have any energy dependence if scaling symmetry is obeyed, right? Because if you so again, I mean, it's very unusual, because when you solve a scattering problem, you always get, if you remember your quantum mechanics, you always get scattering phases which oscillate in some weird way as a function of energy. But in this case, because there is scaling symmetry, you can say that there can be no energy dependence, because if there was an energy dependence, you could apply scaling symmetry and change it, but or more precisely, the energy dependence should be scale invariant, and the only scale invariant energy dependence is no energy dependence, right? I'm sorry, I'm not saying it too well, but anyway, so you don't expect to see any scattering phase energy dependence also, and then from that you can immediately predict various things about scattering. For example, you can predict how conductivity, if conductivity is dominated by scattering on charge impurities, how conductivity which is determined by transport scattering time, will behave as a function of Fermi energy. And surprisingly, you get, using this relation and no energy dependence, you get conductivity which is proportional to square Fermi energy and proportional to density of carrier density. And interestingly, this is what people very often see in graphene, and it's also often attributed to Coulomb impurities. So just from I'm making the point that scaling symmetry is quite powerful. You can draw conclusions from it almost without doing calculation, just based on scaling analysis, right? Including non-trivial things like conductivity. However, if you have no energy dependence, then we don't expect to see any resonances, and we don't expect to see any collapse. And so. So if we have symmetry, if this is scaling symmetry is a true symmetry of the problem, then no collapse. And I think I should stop now. Let me just point out. Yeah, let me show this. So this is an example of symmetry which is in fact broken by ultraviolet regularization, and in that way, so if you remember our discussion or even the work I talked about when people introduced very, very small nuclear radius, which was non-zero, and that was sufficient to change the behavior of the problem, you could introduce a regularization on a scale which was millions, factor of million times smaller than your energy scale, and it would change the behavior over the entire spectrum. So from that point of view, it's similar, in fact, identical to other anomalies. Anomalies is when behavior of a quantum theory changes by introducing ultraviolet regularization, and the change is global. It happens over the entire energy range, not only at the energy scale of regularization, but everywhere. Right, and so there are many anomalies known, including chiral, which was first one introduced, conformal anomaly, gauge anomaly, etc. There was also scaling anomaly, and it's been discussed in high energy physics in various contexts. We can talk about it. And so the point I'm making is that this is a simple example of scaling anomaly. And perhaps this work by Pomeranchuk and collaborators, even though they never formulated in this way, was the first work where anomaly effect has been seen. By introducing your regularization on a ridiculously small scale, you change behavior at a human scale, right? And so what we are talking about here is that type of anomaly. That's point number one. Point number two is that we have a knob here in charge impurity problem, because when we vary impurity charge, we can go from a state where scaling symmetry is unbroken to the supercritical state where it's broken anomalously. There's no spontaneous breaking, but there's anomalous breaking. You suddenly get super high sensitivity to regularization, and it changes the behavior over the entire spectral range. So I think I should stop here and maybe come back to that later. Yeah.
So somehow you just said that when you modeled the experiments, you use a point charge model, but in some sense it was not exactly point charge. No, where is the regulator in your?
Oh yeah. So we no, of course. So you have to introduce some regularization. You always have to introduce some regularization when you solve the Dirac equation. But in subcritical regime, it doesn't matter. What regularization doesn't show up. I'll give examples of that. I'll show.
But in practice, actually, because is it something that you introduce to make integral convergent, or where in practice you have to introduce the regulator in
So after this slide, I have about 5 slides where I give examples, and with there will be a full discussion of it. You can do, for example, I can jump there. So what you can do is, for example, you can add magnetic field. You'll see why I'm doing it, because I want to have a knob for scaling, right? And if I have scaling symmetry, then I can argue that all energies will scale as square root of b, specific way, because there's only one energy scale you can build. And then, so we expect them to scale in this way in the case when symmetry is unbroken, and not to scale when it's broken. And so you can do just numerical simulation. With numerical simulation, you introduce a regularization whether you want it or not, because you have to discretize derivative operator, and then you have some minimal length scale. And so this is numerical simulation with discrete derivative operator, so regularization is built in. However, if you look at the energies which are much smaller than discretization length scale, you see perfect scaling. You see linear dependence versus square root of b, and then when you go to the supercritical state, that's next slide that I don't want to show now, you see that it breaks down. It breaks down even on a scale which is much smaller than a regularization scale. So it breaks down all over the energy spectrum. So that's what we always have for anomaly, right? Right.